Hello and welcome to Chapter 4 in Statistics. We're going to take a look at some key concepts from our PowerPoint notes as well as simulations on StatCrunch. To begin with, just a reminder, if you're looking under your course tools, document sharing, Chapter 4 has some key documents you might want to take a look at. For example, the one activity that we do in class, which has some problem solving. You can also read over those at home and take a look at them, such as Monty Hall problem. You might also notice some other key documents here that might be helpful for Chapter 4. If you have not yet printed your notes guide, please scroll down here and do so. That has some key information for Chapter 4 as well as other chapters in this course, and it helps you kind of organize some of your concepts. We're going to take a look at Chapter 4 here. So if you would turn to these notes if you've printed them and follow along. We're going to start off by talking about, of course, what is probability and different ways to approach it and interpret the values. So an event is any collection of results or outcomes of a procedure. A simple event would be something you cannot break down any further. For example, if you toss a coin, it's heads or tails. There's nothing simpler that we can use to explain that. A sample space would list all the possible simple events. So for example, if you toss two coins, you could have head, head, tail, head, or tail, tail. And if you listed all those, it's called the sample space. And here's one where we look at a single birth, boy, girl, versus three births. So you could have boy, boy, girl, boy, girl, and so forth. And you'll find that it's often helpful to create what's called a tree diagram to kind of keep track of all those so we don't miss them. Of course, we have notation to keep track of. We typically use capital P for probability, and then A, B, and C would denote specific events. So if I write P parentheses A, what I'm really saying is what's the probability of event A occurring. So you have three different kind of approaches to probability, or rules, if you will. Number one, you have what's called the relative frequency or empirical frequency. So in other words, this is actually measuring or conducting a procedure and counting the number of things that happen. For example, in class, we might toss two dice. I'll ask you to record the sums, and you might say, what was your sum of 6? Oh, I got that 5 out of 36 times. That's your relative frequency or empirical frequency. That would be compared then to your classical approach to probability, or your theoretical probability for that, which would be, if you're looking at tossing a 6, that would happen, a sum of 6 would happen 5 out of 36 times, because you would say, how many ways could that occur out of the total number of ways? Of course, you also have subjective probabilities where you're using information as well as personal judgment to make a decision or to estimate information. We also have what we call the law of large numbers. As you repeat a procedure over and over again or do a larger sample size, your relative frequency will tend to approach your theoretical or predicted probability. And again, some examples for you to read over. Now, we're going to be taking a look in this chapter at simulations, and it's a process that works in the same way as doing the experiment yourself, so that you get similar results, but of course the computer takes off the onerous burden of us sitting and tossing a dice, for example, 3,000 times, or picking poker hands 5,000 times to find out what the chance of royal flush is. We'll take a look at some of that in StatCrunch. Probability is always going to be between values of 0 and 1, 0 meaning it doesn't happen or it's impossible, 1 meaning it's certain to occur, it happens all the time. So again, anytime we're noting a probability, it needs to be between 0 and 1. Something that's impossible is going to have a probability of 0. Something that's totally possible or certain would be 1, which is kind of cut off here on your screen. And of course, likely gets closer to 1, unlikely gets closer to 0. Complementary events consist of all the outcomes in which the event A does not occur. And you'll find yourself using that in this chapter a good deal. For example, we might say if a family has 4 children, there are 16, 2 times 2 times 2 times 2, possible orders of boys and girls. Now, only one of those orders would be all boys. So the other 15, or the complement, 15 out of 16, would be some combination of boys and girls. And here again, if you found the chance of a smoker was 20%, the chance of finding somebody who was not a smoker would be 80%. Again, pay attention to round-off rules, particularly doing your My Math Lab homework. Read the directions, pay attention to those. Sometimes you're asked to give a fraction, sometimes you're given a decimal. Again, if something is very unlikely to happen or unusual, it's going to be less than 5% of the time. Now, just in case you thought probability and odds are the same thing, let me clarify that. They are not. Probability is part out of the whole. Odds are what are you looking for compared to what's left, or the complement? So if I say the odds against event A, I'd be saying, well, what's the chance of A not occurring compared to the chance of A occurring, and then it's reduced. Or the odds in favor would be the chances of A occurring compared to what's left. At the bottom of the screen, then you'll find out how to kind of compute payoff odds, just in case you need to know that information for a little horse betting, perhaps. Here you are at the casino, and you want to bet $5 on a number 13 on roulette. Your probability of winning is 1 out of 38. That means there's one way to win and 37 ways to lose. So we want to know what are the odds, and then of course what net profit you get. So 37 to 1, as we already mentioned, are the ways to lose. And the payoff odds are 35 to 1. That means you have a $35 profit for every dollar you bet. So if you would bet $5, you can make $175. So the winning bettor would collect $175 plus their original $5 bet. Okay, let's take a look at section 3, the next section in our material here. This is where we're going to discuss the concept of the addition rule when you're asked to compute probabilities for one or the other event. The key word in these problems is or. It's an inclusive or, which means you could be A or B or both. And when you're doing the one where both occur, you're going to need to remember to subtract off overlapping probability at the end. So basically what we're looking at is what is called a compound event, any event that combines two or more simple events. And you want to make sure you don't count an outcome more than one time. So your formal rule, for those of you who like a rule or a formula, is the probability of A or B is the probability of A plus probability of B minus any possible overlap. Or intuitively, you're basically adding A and B, being very careful not to count any event twice. Events A and B on the right-hand side here in this picture are not overlapping at all. We call that mutually exclusive. However, on the left-hand side, they are not mutually exclusive. They are overlapping. And there's some area here you can see is kind of orange between the reddish pink and the yellow. That area indicates the probability of A and B, where they both are occurring at the same time. If you want to compute complementary events, of course, A and its complement are going to have to be disjoint. You cannot have both at the same time. So complementary events are going to add up to 1. The probability of A, the chance that it is snowing while you're looking at this, is 40%. Then the complement is 60%. And 0.40 plus 0.60 would add up to 1. This would be a classic picture for a complement, A or outside A, but you can't be both. Okay. In our next section, we're looking at the multiplication rule. In the multiplication rule, we're looking at problems where we're looking at P of A and B, or two things in a row, or possibly even a conditional kind of probability where we're saying, what's the probability of B given that A already occurred? So you're going to be multiplying probabilities. So especially if you do the given that or the conditional, you want to be sure the probability of event B is considerate if something else had to happen first, if A happened first. So again, if we have several events, we're just simply going to multiply their probabilities. Now, key terminology here, independent versus dependent. Two events are independent if the occurrence of one does not affect the probability of the other occurring. For example, a couple gets married, they have a little girl, a couple of years later, they're pregnant again, they have a little boy. Those are independent events. The birth of one child does not affect the birth of the next child, the gender of the child. If, however, two events are dependent, that means somehow the one affects the other. So, for example, you have a jar with marbles in it, and you pull out a blue marble and you do not replace it. Well, you've now changed the total number of marbles in the jar, and your chance of picking another blue marble has been affected. Those two would be dependent. We do have what we call a 5% guideline. If your sample size is less than 5% of the population, you can basically treat your selections as being independent because basically you're using such a tiny piece of a larger population. Here, for example, suppose 50 drug test results are given from people who do use drugs. 44 were positive, 6 were negative. If you pick 2 of the people without replacement, find the probability that the first person tested positive and the second tested negative. So the positive test result for the first person is 44 out of 50. Now, the second test result is 6 people had negative results, but there's only 49 left because you already picked somebody. So you have 44 out of 50 times 6 out of 49. And that's because it's selected without replacement. Now here, of course, is that infamous birthday problem. If we pick 2 random people from a class, what's the chance that 2 people would be born, for example, the same day of the week, or, for example, have the same birthday, day and month? And this is always one that's a good problem to simulate. Take a look at on StatCrunch and spend some time thinking about it. Now, part A here just says, what's the chance that 2 people were born on the same day of the week? So we can pick any day, because we didn't specify which day. So the chance that the first person was born, and the chance that the second person was born is 1 out of 7. So the chance that both are born on the same day is 1 out of 7. But we're saying, what's the chance that they're both born on a Monday? Be 1 out of 7 times 1 out of 7, or 1 out of 49. Now, a tree diagram, I mentioned this earlier. This is a way to kind of show the pictures, to show what happens. So, for example, here we are. We're going to take a little quiz, 2 questions in class. The first question is true, false. So there are 2 possible outcomes. The second question is multiple choice, A, B, C, D, E, 5 answers possible. So you could have a true and an A, or true and a B, or true and a C, or true and a D, so forth. So you can kind of see the different possibilities. Because there's 2 choices on the first question and 5 on the second, there are 10 possible outcomes listed to the right. Again, remember the word or indicates addition. Remember the word and indicates multiply. And this little chart here kind of helps us summarize that for the multiplication rule. Okay, taking a look at our next one. Again, remembering the concepts here, we're looking at the multiplication rule and the possibility of conditional probability. Some key verbiage to watch for are things like at least 1 or at most 1 or no more than a certain value. So, for example, at least 1 is equivalent to me saying 1 or more. And the complement of that, of course, would be that you got none. To find the probability of at least 1 of something, it's often easier to simply say, well, let's assume that it didn't happen at all. What's the probability of that? Subtract from 1, and then I know that what's left is the chance of 1 or 2 or 3 or 4 or more. So for example, you have X-ray DVDs, or X-data DVDs in lots of 50, and they have a reported defect rate of 0.5%, meaning the chance of a disc being defective is 5 out of 1,000, 0.05. So therefore, probability of a good disc is 0.995, and we want to know what's the chance of getting at least 1 disc that's bad in a lot of 50. Well, it's easier for us to assume that they're all good and subtract from 1 to find out the chance that 1 of them will be defective. So we find the probability that all of them are good, which would be 0.995 to the 50th power, and we subtract that from 1. This is the chance that they're all good, 0.778. So the chance that something is wrong somewhere, or more than 1 is wrong, is what's remaining, or 0.222. Again, looking at results with a drug test, we want to find out the chance that somebody had a positive result. But now we're saying, find the probability that they actually use the drugs, given that they had a positive result. Oh, we might want to go back and reread that. Students typically get frustrated with these problems because there's a condition in here, and sometimes we miss a part or we read it backwards. So again, find the probability that a student actually uses drugs, given that they had a positive test result. Oh, okay. Well, that means we're only looking at the positive test result column. Out of these 134 people, how many tested positive? And the answer is 44 out of 134, or 0.328. And be very careful. Do not assume that P of A given B and P of B given A are the same. In other words, if we went back to the drug testing table, we can't say that the chance of them using drugs given they had a positive test is the same as getting a positive test given that they use drugs. They are not the same. And that is what is called confusion of the inverse. So be very careful when you read those questions. Okay. Lastly, we want to take a look at counting here before we look at simulations. And the counting rules, the fundamental counting principle is the first one. These are nice rules, nice to use. So for example, if you have a sequence of events in which the first gets so many choices, the second has so many choices, you can multiply that to find out the total number of possibilities. And as we begin to work in these problems, we also have a little bit of notation here, this factorial symbol, the exclamation point. This doesn't mean 4. It means 4 times 3 times 2 times 1. So for example, if you had 4 items and you wanted to arrange them and you wanted to know how many possible orders there are, initially you'd have 4 to pick from, then you'd have 3, then you'd have 2, then finally the last slot you'd only have 1 to choose from. So the total number of arrangements is 24. And keep in mind, of course, if you had 0 items, there's only one way to arrange them. There's nothing you can do. So the default for 0 factorial is 1. We can also talk about permutations of items. So you want to read through these. Permutation rules when items are different. If you have n number of items and you want to select r of those items. Permutation order counts. Order is somehow critical. So for example, if it's a contest where it's first and second place, or it's a writing competition where first prize is $500 and second prize is $250, or it's a beauty contest, or it's president and vice president, anywhere where order counts, you're dealing with a permutation. You should definitely be using a calculator for these problems. You can use a TI-30 looking for your PRB button. Then you have built-in permutation and combination functions. If you're using a TI graphing calculator, you will first need to go to your math functions and choose PRB. Okay, if you do have items that are being arranged, but you have some repetition, for example, like Mississippi, then you have the total number of letters arrangements on the top, but you're going to divide out the repetitions. And you'll see some examples of those in our notes. For combinations, you have n items, you're choosing r, but here order does not count. I'm not concerned about order. For example, if there are 50 numbers to pick from and I have to pick 5 to play the lottery, but the order doesn't matter, then it's a combination problem. And again, I'm going to be using my calculator to help me solve this problem. Again, just to review, if order counts, it's permutation. If order does not count, it's a combination. So, the history pop quiz asks you to arrange the following presidents in chronological order. So you have Hayes, Taft, Polk, Taylor, Grant, and Pierce. If you guessed completely, there are 720 different orders that this could happen in. That's a factorial. And there are, of course, only one set. There's only one set of correct answers. So 1 out of 720 is your chance of getting them all right. In the Pennsylvania Match 6 Lotto, winning the jackpot requires you to pick 6 different numbers from 1 to 49. They can be in any order, so it's a combination. You'll see the problem here is worked out for you. Now we're going to take a look here at StatCrunch, and we're going to briefly run through an applet. So you're going to choose simulations, and you can, for example, go to dice rolling, and like we do in the face-to-face classes, for example, if you toss 2 dice, and you want to see, for example, what's the chance that you get a sum of 7. Now in class, we do a small sample. We only do 36 tosses, and we're going to find out some variability from the predicted values. But when we can use the simulation, we can take a look at much larger sample sizes and considering the law of large numbers. So let's do 2,000 runs, and you can take a look that a sum of 7 happened 16.3% of the time, which is pretty close to the theoretical value of 0.166. Repeating. Run it another 1,000 times or 2, and you'll notice that we're getting even closer to that 0.166. Okay. We have other simulations as well. If you've thought about playing poker recently and you want to take a look at whether or not you should bet on a full house, well, let's take a look at a simulation of those. Typically you have a 5-card hand. We're going to simulate 1,000 games with 5-card hands, and your chance of getting a full house is 1 out of 1,000. Probably not a good idea to bet on that. How about 4 of a kind? Is that a better chance? Not really. How about a straight flush? Probably shouldn't play that one at all. Maybe a straight. Well, that's slightly better. 8 out of 1,000. 3 of a kind? 1.2% or 12 out of 1,000. How about the chance of getting 1 pair? Well, you might be okay if you bet on that. That's going to happen about 47.8% of the time. 2 pair? Already unusual, less than 5% of the time. Some other applets we can take a look at here. The birthday problem. This is always a good one. So think about this. If you had 30 students in a class and you wanted to know what's the chance at random that you would have a shared birthday in your class, by that we mean day and month. So for example, somebody says, well, my birthday's May 12th, and another student says, that's my birthday too. What do you think the chance is that that would happen? Well, let's simulate 1,000 classes of 30 students, and you'll see that there's almost a 40% chance that there would be a shared birthday in your class. What about a chance of 2 birthdays being shared? Well, there's still a 23.7% chance, and this is often way higher than students anticipate. So stop and try to think about why that would happen. Okay, you can also take a look at coin flipping, raffle winnings, and urn sampling. Now up here under experiment, you can actually go through and do some simulated experiments yourself, drawing cards, doing the birthdays, rolling dice, or flipping coins. Again, if you do this, I'm just going to do 10 tosses here. Then when you click Analyze, it will copy your data directly into the table. And then you could do something even like run a quick histogram and take your coin flips. It's not showing up right now. Well, it should be showing up, and you should be able to take your coin flips and then click to compute, and it will give us a nice little graph. Okay, hope that's helpful. Good luck in Chapter 4.